Hi, this is Pre-Calculus, and we're dealing with rational graphs, or graphs of rational functions. And so we want to start dealing with asymptotes, vertical, horizontal, and slant, holes, intercepts, and domain. If we get all those things, then we can go ahead and graph. So to start off with this preview, what we want to do is look at limits as x goes to infinity. Use your table or a graph to estimate each. So what we want to do is look at this first one, and then I'm going to ask you to do the second and third one, and maybe even the fourth one, and go from there. So what we want to look at is what happens as x goes to infinity of this rational function. What does f of x look like? Or what does f of x approach? So if I graph this thing, I've already put it in. You should put it in your calculator. I look at this. This looks like it flattens off. If I zoom out just once, so if I zoom out, or maybe twice, what happens to my end behavior? And that is what we're talking about. Well, this looks like a straight line. What is your end behavior? Well, I think it's going to be looking like a straight line. I can't tell for sure, but that's what it looks like. Well, what value are we approaching? So what we need to do is go to a table. So I'm going to go menu and go to table and put in my split screen here. And if I put in a big number, and I don't even have to go that far, but it does look like I start approaching the number 1. And I could continue to do this for a long, long time. And it looks like as x goes to infinity, so these are my x values. As they get bigger, what happens to your y values? Well, they get closer and closer to 1. So what we say then is our end behavior is 1. And more specifically, we would say that this behaves like y equal to 1, which is a horizontal line. Now, similarly, I can go the other way to negative infinity. What happens as x goes to negative infinity? Well, when x goes to negative infinity, I'm going to be approaching 1 as well, but I'm approaching from the underside. So this one approaches from underneath. This one approaches from the top, and it does approach 1. You can even go out here to 1,000,000,000 and see that that does work for us. So now going back to our note sheet, what happens here? Well, we say that f of x approaches 1. So what we call this then, and I'll define this a little bit later, we call this the horizontal asymptote. You should be familiar with this. And it's the horizontal asymptote is always an equation. Y equal to 1. Please do not tell me that the horizontal asymptote is 1. It is y equal to 1. I think I might have even said 1. That's wrong before. But y equal to 1 is the horizontal asymptote. Go ahead and graph these two and see how these two turn out as far as their end behavior for big X. Okay, I paused. Did you pause? You should have gotten values. If I look at this one, I'm going to do it analytically, or it's not perfectly analytically, but it's how do we look at this thing. If I plug in really big numbers here for X and I square them, what's going to be the significance of these two values? Well, 1,000,000,000 squared will drown out this 2 times 1,000,000,000. And this 3 will be left in the dust. So in other words, over time, these two will become insignificant as we are approaching infinity. Similarly, down here, these two will become insignificant. So really what I'm looking at is that as long as this degree is the same, I can take the leading coefficients from both of them, and that's what I'm going to end up approaching. And I think that most of you should have gotten 1.75. I hope you did. Or 7/4, and that's what you are approaching as x goes to infinity. So if we wrote our horizontal asymptote here, it would be y equal to 7/4. Similarly, down here, example number 3. Can you do this? And you can't just cross this stuff off. You can look at it in an analytical way and say, oh, my leading term here is a 3 and it's x cubed. My leading term here is a 2 and it's x cubed. They're going to grow kind of the same. These parts are insignificant, so this is going to be 2/3. So just take the leading coefficients and you're in business. So this would be y equal to 2/3. Now, what happens if I don't grow at the same rate? Looking at example 5, the denominator grows faster than the numerator. Well, let's think about what happens when I get 1 over a big number. 1 over 1,000,000,000. Oh, that's a very small number. What about 1 over 0.0001? Well, that would be a big number. We got to think about those things when we're doing this. So what happens here is that, yeah, both of these are getting big as x goes to infinity. However, this denominator is growing much faster. And so as the denominator grows much faster, I'm going to get smaller and smaller. And so what I say is that this would approach 0. So the horizontal asymptote, whenever the degree on the denominator is bigger than the degree on the numerator, then we're going to go to 0. Bottom's growing faster than the top. Boom, 0. Okay? Those are horizontal asymptotes. Now let's define this stuff and kind of do the nitty-gritty parts. If we take a rational function or rational expression, that means that we have some polynomial divided by another one. We're going to call n for the numerator, d for the denominator, and d is not the 0 polynomial. The times that we look at domain then. Domain in general includes all real numbers except for, where's the problem? Yes, when d of x is equal to 0. All x values where d of x is equal to 0 would not be included in my domain. Let me repeat, would not be included in my domain. Otherwise, we can fit everything else in. Vertical asymptotes usually occur at these points. So as x approaches a, that means that f of x goes to infinity or f of x goes to negative infinity. I should have maybe written that the other way around, but let's look at this. Vertical asymptote would occur right in here. That would be at 3. X equal to 3 makes this denominator 0. But the definition of a vertical asymptote is that my behavior in and around 3 is going to go to either positive infinity or negative infinity. It depends which side I'm coming from. I'm going to modify my table and change the settings a little bit. I want to do a t-step of 0.01. And so I want to get close around 3 and see what happens. So if I go OK here, I'm at 1. Yeah, this is -1. That isn't so big. And I get to about -2. Then I'm at -3. That isn't so big, negative. But look what happens as I start getting closer and closer to 3. This really starts dropping off. And in fact, I go from 2.98. The y value is -199. I go 1/100th more. Ooh, it really jumps to -399. So if I go 2.999, I'm sure that it's going to go way big negative here. All right? So what happens is that from the left-hand side, this is the left-hand side that I'm approaching here, I'm going to go and drop off to negative infinity. That's my y value. F of x is going to go to negative infinity. What happens as my x approaches 3 from the right side? Well, as x approaches 3 from the right side, I'm going to approach positive infinity, and that's the y values going up here. So you can zoom in on that and see what the behavior is like. So I should say as x approaches a, then f of x approaches positive infinity, or f of x approaches negative infinity. Now what they do sometimes is they put direction on here. So after the a, you can put a plus, which means from the right side. So if I go x approaches a, that means from the right side, and x approaches a with a negative after it, that means from the left side. So we can get even more specific if we want. We'll leave that up to your teacher. Okay, then horizontal asymptotes, the line y equal to b. What is our end behavior? Well, it looks like a horizontal line. Not perfectly, but pretty darn close. That would be y equal to b. And then we have a horizontal asymptote as f of x approaches b as x approaches infinity or negative infinity. And so this behavior is very similar to a line. So y equal to b, that's what it would be similar to. Now a slant asymptote is a situation that we did not cover in our introduction. This is where the degree of the numerator is 1 higher than the degree of the denominator. Well, think about it. If I take a cubic, x cubed plus 3 divided by a quadratic, x squared minus 4. Cubic divided by a quadratic is going to give you a linear. And that's what's happening, is that my end behavior is going to look like a line. So that might be like y equals mx plus b. Most of ours will just be y equals mx, but you might have one that looks like y equals mx plus b. All right, so that's slant asymptote. And then a hole occurs when the factors, it's going to mean that we're going to divide by 0. We're going to have a problem. But how does this happen? When the factor of n of x cancels with the factor of d of x. So if n of x, one of the factors cancels with one of the factors of d of x, then we're going to end up with a hole in the graph rather than a vertical asymptote. Okay, so let's get into some examples and see how this goes. First of all, this number 1, we want to see what the domain is. Well, I hope that you can tell by the denominator. For the denominator, x can't be 3. If x is 3, then we have an undefined function. This is going to be a vertical asymptote because I have no factors that can cancel here. So I'm going to do this. Now the trick is, well, I'll get to that. And then identify any intercepts. My y-intercepts would be when x is 0. When x is 0, I get 1/3. So this would be 0 and 1/3. That's my y-intercept. How about zeros? When y is 0, I'm going to get 0 equals -1. There are no x-intercepts or any zeros then. Plus my numerator is not 0. That's what you look for. Okay, so that gives me a point, 0, 1/3. So that's going to be right here. Asymptotes, we have already identified one vertical asymptote. That would be x equal to 3. So if I ask you what is the vertical asymptote, don't tell me 3. It's x equal to 3. What about horizontal asymptote? What's our end behavior? Well, as x goes to infinity, this denominator is going to get really big. The numerator is negative, but regardless, then f of x is going to go to, was something over a big? Well, it's going to be a small. Okay? So our horizontal asymptote then would be y equal to 0. And that doesn't matter if x goes to positive infinity or negative infinity. So I have a horizontal asymptote here at y equal to 0. Now, I never said that I would cross the x-axis, so it looks like I'm going to approach this horizontal asymptote from the top because I can't cross the x-axis. I didn't find any zeros. And I have this point above the x-axis. So which is the only way I can go? Boom, it looks like I can only go there. Now let's double check. How you double check is that you can do a little sign chart. And so what I want to look at is what happens in and around 3. So in and around 3, if I come from the left side, think of a number like 2.9. If I take 2.9 here, just figure out the plus and minuses of what's going on. So if I take 2.9, I have a negative on top, and I'm going to have a negative on bottom. What's a negative divided by a negative? Well, I'm going to have a positive value. At 3, we have a vertical asymptote. And then on the right side, what about when I plug in 3.1? 3.1 will make this denominator positive. What's a negative divided by a positive? Well, that's going to be a negative. Now, since I know that x equal to 3 is a vertical asymptote, and I check a point here that's going to give me a negative that's really close to it, that means that I'm going to approach negative infinity from the right side. Here, this means that I'm going to approach positive infinity from the left side. So I know I'm going to be here. So really all you do is check a point in and around this vertical asymptote. Positive, it's going up. Negative, it's going down. And then I don't cross over this thing anyplace. So I go like this. Now you can check some other points to plot in here. Or you can check this on your calculator, but this is what it should look like. And then if we do graph this, we see that we're correct. All right, so you can check it with your calculator. Now, going to the notes again, the next example, let's see what happens with number 2. Number 2 will be a little bit more interesting because we can factor. For you people having trouble factoring, I don't know, we got to get you some practice somehow, so you should ask for some. X minus 5, now watch me make some mistakes. X minus 5 over x plus 3. That's what I see here. Factors of the last are 5 and 3. This one negative gives me that one negative. And then this one would be x minus 3, x plus 3. Now what happens is that right now, my domain, that's what I want to look at first, is going to go from negative infinity up to negative 3, and including negative 3 to 3, and then including 3 to infinity. However, at negative 3 and 3, I'm going to be undefined. Now here's the problem though, and it's not really a problem, but I can cancel these two. So what happens is that when I can cancel these two, this function is going to behave like this one right here. Everywhere except for at x equal to negative 3. What happens there? Well, this turns out to be what we call a hole. So you're going to graph this part right here. And then you're going to take a little white out, and at x equal to negative 3, and you're going to just make a hole. So that's what we're going to be doing. So here, once again, we have a vertical asymptote at x equal to 3, because that's the value that makes this piece 0. X minus 5, I have a horizontal asymptote at 1. This one's very similar to some of the other ones that we've been doing. So I should keep on going. Vertical asymptote would be y equal to 1, because numerator and denominator grow the same, or else I can even do it over here. And then my horizontal asymptote, boy, did I just do that wrong, y equal to 1. I want this vertical asymptote to be x equal to 3. Sorry about that. And so vertical asymptote is x equal to 3. Horizontal asymptote is y equal to 1. And then we can figure out our behaviors a little bit. I think this one's going to look much like the other one. I'm going to be positive here. Now let's check to make sure that this is right. As I get close to 3, plug in 2.9. I get a negative when I plug it in here. 2.9 minus 5 is negative. 2.9 minus 3 is negative. What's a negative divided by a negative? Yes, a positive. So with a little sign chart here, at 3, I'm going to get a positive, and then I'm going to get a negative on the other side, I bet. Because if I take 3.1, this is going to be negative. This one's going to be positive. So a negative divided by a positive is a negative. Now I did miss a y-intercept here. Let's see if we do have a y-intercept. So what I do is I set 0 equal to x minus 5 over x minus 3. So for my x-intercept, I'm so sorry, x-intercept, let y equal to 0. I cross multiply, the x minus 3 goes away, and so it's just the numerator tells me that I have x equal to 5. Look at that, I hit it spot on. So I do have an x-intercept of x equal to 5. Y-intercept, I never checked, but if I plug in 0, I'm going to get 5/3. So this point right here would be 0, 5/3. So that's my y-intercept. Okay? So that gives me a pretty nice graph. You can check that with your calculator. Now the next couple, now look at the degrees. The degree of the numerator. The degree of the numerator is 2. What's the degree of the denominator? 1. So the degree of the numerator is 1 greater than the denominator. When you see this, you should say to yourself, we have a slant asymptote. What's our end behavior? Well, our end behavior is going to be a line because I'm taking a quadratic and dividing by a linear. So if I do this, I just divide this. You can do long division, but in this case, since I have a monomial here, I can just do the rabbit method. So I'm going to rewrite this as y equals x plus 5 over x. Now what happens with the slant asymptote? When you divide these things, this would be your end behavior, because as x goes to infinity, this thing will behave like y equal to x. Why? Why don't I include this anymore? Well, think about it. If I take positive infinity and plug it in here, that's 5 over a really, really big number. Well, that makes this go to 0. So this is going to behave like y equal to x. And so what I do then is I make a slant asymptote at y equal to x. That's going to be my end behavior. Now the question is what happens at other places? So our domain, what is our domain? Look, we can't divide by 0. So this would be x can't be 0. And then, so that's my vertical asymptote. I got this here. Now what you might want to do is just find some points that might work for this thing. Let's see about y-intercept. Y-intercept, I've been messing this up. I'm going to let x equal to 0. I'm going to write this out more. Would be none, because we just have a vertical asymptote there. X-intercept would be y equal to 0. So if I let 0 equal x squared plus 5 over x, that means that x squared plus 5 is equal to 0. Oh, there's no values of x that work for that. So there's none for that either. Okay? So there is no x-intercept either. So what I need to do is maybe find a point. So let's take, for instance, 2 and plug it in here. If I take 2 and plug it in here, I'm going to get 9 over 2, 4.5. So if I plug in this point right here, I'm going to get 4.5. Also, I can test my vertical asymptote with the sign chart. So at x equal to 0, which way am I approaching? Well, from this side, from the left, if I approach 0, for instance, negative 0.5, well, that would be a positive number, and that would be a negative. Positive divided by a negative is going to be a negative. So I'm going to be approaching negative infinity on the left side. Right side, if I take in 0.5, that's going to be positive divided by positive, and so I'm going to approach positive infinity. So I know straight away that my behavior there on the right side is positive infinity, left side is negative infinity. Now my end behavior is like this. So I think I'm going to come down here. I don't know how far down I'm going to come exactly. Maybe I need to plot a few more points, but I think I'm going to go like that. That's about all I can do. You can maybe plug in -2 or -1 to get a better idea, but that's what my graph is going to look like. Okay? Now you might say, how do I know? Well, I do know my end behavior, and I do know my behavior here, and I picked a point. So I have to kind of connect up these pieces to make it work. All right? Now the last example, what you have to do to find, I'm just going to find the slant asymptote, and then you can graph this because this is getting quite long. The slant asymptote, look at the degree, 1 higher than the denominator. So I'm going to do long division, x cubed over 2x squared minus 8. So I need to plug in all my pieces here. And so I look at the leftmost term, and that looks like I'm going to have to multiply by 2x. And so if I multiply by 2x, I get 2x cubed minus 8x. And then I subtract. This is not a good day for me. Let me try this again. I need to match up this x cubed, so I need a 1/2 x. And so this would give me x cubed when I multiply these two together. And then I got to go minus 4x here. Then I subtract. These go away, and then these two here would become positive 4x. And so what happens with this is that I can take this, since this is smaller than, the degree is smaller than this one, I have to take this remainder, 4x, and divide it by the divisor, so 2x squared minus 8. So what happens as x goes to infinity, this thing is going to become 0. So really the slant asymptote is simply y equals 1/2 x. I'm going to let you graph that with your calculator and then see how that one turns out though. So you do long division for the slant asymptote, and you just take this piece, and the remainder you can kind of ignore, but that would be what your slant asymptote becomes. That's your end behavior. As x goes to infinity, this becomes 0. All right? This is really long. I apologize. I hope you split this up and took a little break, and but a lot of information. Well, thanks a lot. Have a good day.